Welcome. In this lecture video we are going to talk about projectile motion, and we're going to focus on simple projectile motion. And first we're going to look at the concepts involved in dealing with problems that have projectile motion in them, and then we'll do a couple example problems. So here let's say we have a projectile that's launched from the ground and it comes back to the ground. We have a time axis on the bottom here, 1, 2, 3 seconds. It's in the air and it looks like it goes to a height of a little bit more than 10 meters. So when it's launched, we can look at the initial velocity, and that initial velocity is going to be going off and tangent to our graph here. So this would be v0, the velocity of launch. And now what we've already looked at is that we can look at the horizontal component of the initial velocity, and we can look at the vertical component of the initial velocity. And as this thing moves over time, we've talked about the fact that we can separate out the horizontal motion from the vertical motion. Horizontally, if we ignore air resistance, we have no acceleration. So that v0x, this guy right here, will never change. The x component of the motion is always going to be the same. So if I drew it in at the very top, that v0x is still the same length pointing horizontally. And if I drew it at the end over here, that v0x is still going to be the same length. There is no acceleration in that direction. If I drew it right here, v0x, same length. If I drew it here, v0x, same length. All right? Never changes. Any changes are due to my inaccuracies of drawing. Now in the y direction, we have a freefall problem. This ball is launched, it goes up, comes to rest at the top, and it comes back down. There's symmetry in this. So at the very least, we can say at the top, up here, at the very top of the arc, there is no vertical velocity. The vertical velocity is 0 instantaneously right there. So our whole velocity at the top is just horizontal. And when it hits the ground over here on the right, then we can say that just like in those freefall problems, we get to use the symmetry of the situation. And that should have been about the same length as the other one I drew. Over here, this v0y, it's going to be the same magnitude, just going in the opposite direction. So this is negative v0y over here. That's the final velocity when it hits the ground. So if I add those two vectors together, v0x and v0y, remember we always add those vectors tip to tail, I should get a final velocity vector that is equal in magnitude to my initial velocity vector, just pointing in a different direction. Instead of being some angle above the positive x-axis over here, that angle theta, we are some angle below the positive x-axis over here. Same angle, theta. All right? Other things to conceptually think about here, if we look at these two green points on our graph, we're going to have some initial vertical velocity, or not initial, some vertical velocity that's less than our vertical velocity was at the start. Ball's on the way up, it's slowing down. We know at the top, no vertical velocity. But here, we've got a little bit of vertical velocity. So combining those two again, using vector addition, we've got a velocity that looks like that. Over here on this side, on the right, our vertical velocity is going to be identical to what it was over on the left at that same elevation. And so we've got some velocity going down that way. The magnitude of those two velocities at the same elevation should be the same. So the bottom line here is we are going to treat the vertical motion and the horizontal motion separately. Vertically, we have acceleration, negative 9.8 meters per second squared downward. Horizontally, we have no acceleration. So in every projectile motion problem, we're going to separate these two, vertically and horizontally. Vertically, we remind ourselves we have an acceleration equal to negative 9.8 meters per second squared the whole time. Horizontally, we have an acceleration equal to 0 meters per second squared. There is no acceleration. So vertically, we know since the acceleration is constant, hey, great, we get to use the kinematic equations. So we've got y final equals y0 plus v0 times t plus 1/2 a t squared. We have v final in the y direction is equal to v initial in the y direction plus acceleration times time. And we have v final squared is equal to v naught squared, and this is both y and y, plus 2 times a times delta y. All right, the acceleration in all three of these equations is going to be negative 9.8. Horizontally over here, take a look at these equations. Every single one of them has an a in it. So the middle equation doesn't apply. It gives us an uninteresting v final equals v naught when we look at the horizontal motion. Same thing for the third equation. The acceleration is 0, so this term right here cancels out. V final equals v naught. Those two equations don't help us out at all horizontally because there is no acceleration. So the only equation that means anything horizontally is x final equals x naught plus v naught in the x direction times time plus 1/2 a t squared. And again, since the acceleration is 0, that term is 0, so we really end up with only one equation, one kinematic equation to use for the horizontal part of the velocity. And I'm not even going to call it v naught x because the velocity in the x direction doesn't change. So let's just call it vx of t. So only one kinematic equation in the horizontal direction because there's no acceleration horizontally. We get to use all three of them in the vertical direction, remembering that the acceleration is negative 9.8. So as a result, vertically, we've got all 6 of the variables that we've classically used. We've got y naught, we've got y final, we've got v naught, and I'm specific here, in the y direction. We have v final in the y direction. We have a, and we have t, remembering that a is always negative 9.8 here. Over here in the x direction, we only have 4 variables we have to worry about. X final, x naught, velocity in the x direction, and the time. Really important to remember that when I do a variable table that includes the whole motion of the projectile, those 2 times are the same. Okay, so the time that it goes horizontally is the same as the time as it goes up and comes down. All right, so strategies for these problems. Draw a picture, always. Second, fill out a variable table for both the vertical motion and for the horizontal motion. Third, figure out how you're going to use the kinematic equations to solve for the unknowns in the problem. Let's look at an example. So here's our example. We've got a projectile that is launched from the ground at a velocity of 10 meters per second at an angle of 60 degrees above the positive x-axis. So we're going to ask 2 things about this projectile. How high does it go? And we're also going to ask how far. Okay, so y max is how high, and x final is going to be how far. All right? So we've already drawn our picture. The other really important thing that we should probably do is resolve our velocity vector into its x component and its y component. All right? So we do have a right triangle here, moving that vy over here, and vx is the side adjacent, so we end up with a component that is 10 times the cosine of 60 because that's the side adjacent, and on the y side it's the side opposite, so we're going to be 10 times the sine of 60, sorry, for the y component to our velocities. So we actually have magnitudes here for vx and v naught in the y direction. All right, so now we're going to fill out some variable tables. And first, let's see, we want to know how high the projectile goes. So I'm going to fill out a variable table for x and y that just talks about the first half of the projectile's motion, just the way up. All right, so we're just talking about the way up. And I'm going to do the x over here, the y over here. So let's see what we come up with here. Our initial position, let's call that the origin, 0 meters. Our final position is unknown. The acceleration, there is no acceleration. Velocity in the x direction was 10 times the cosine of 60, which is 5 meters per second. And the time that it takes to go all the way up to the top is also unknown. In the y direction, we have y initial. It's launched from the ground, so we're going to call that the origin as well, 0 meters. Y final is unknown. It's what I'm trying to find, so I'll put an exclamation mark. V initial in the y direction is equal to that 10 times the sine of 60, and an approximation of that is 8.66. So we'll use that decimal approximation in our work. V final in the y direction, here's where you have to use your brain. Remember, we're just talking about the way up. At the very top of the projectile's motion, it has no vertical velocity. So I can fill that in, 0 meters per second. The acceleration is negative 9.8 meters per second squared, and the time that it takes to go all the way to the top, unknown. All right, so there's our two variable tables. We are looking for y final. Okay, so kinematic equation that has y final in it but doesn't have time. Oh yeah, v final in the y direction squared is equal to v naught in the y direction squared plus 2 times the acceleration times delta y. That's what we're looking for right there, delta y. What is the y displacement for the way up? So filling in what we've got, v final is 0 squared equals v naught 8.66 squared plus 2 times, remember it's negative 9.8 times delta y. So we're going to solve for delta y. We get negative 8.66 squared divided by the quantity of, let's just say it's negative 2 times 9.8. That's going to give us the same thing, and that's going to be delta y. Let's plug this into the calculator, and we get a delta y is equal to 3.83 meters. So that is our answer for how high. 3.83 meters. This could be a soccer ball kicked up in the air. How far does this go? Now we're looking for this entire x distance. We're looking for x final, and we're not looking for x final just for the way up, because x final just for the way up would be only half the distance. But here's the trick. We could still use this variable table that we already have developed. If we find half of the total horizontal distance, we double it. That'll get us the answer that we want. All right? So we have a problem, though. Over here, I cannot use my kinematic equation in the x direction because I have two unknowns, x final and time. That's where the fact that these two times are the same comes in. So if I can solve for time over here, then I could go ahead and plug it in on the x side, and I could get my answer for x final. All right, so let's go ahead and do that. We've got the simplest equation on the y side is v final in the y direction is equal to v naught in the y direction plus a times the time. So I can use this with my newfound understanding of, well, no, I already knew what the velocities were. I can use this to find the time that it takes to go up to the top. All right, so let's do it. V final y minus v naught y divided by a is equal to t. Plugging in numbers, we have 0 minus 8.66 divided by negative 9.8, and that's going to give us the time. And we'll plug that into the calculator. We get 0.88 seconds is equal to the time. We've got to be careful, though. That's the time just to go up. So we have two options. I can double this time and then plug it into the horizontal kinematic equation, or I could plug it straight in and double the distance that I get. Either way, I need to be very careful and make sure that I'm not just talking about that distance right there. I want the whole distance. So either double the time and plug it in, or plug in that time right here, and then we'll double the x final that we get. So let's just go ahead, and t total for the whole flight is going to be twice that, which is going to be 1.77 about. And we're going to use that in our kinematic equation for the x direction. X final equals x naught plus vx times the time. So we're solving for x final. Great x final is equal to x naught, which is 0, plus velocity in the x direction, which was 5, going back to our table. Remember velocity in the x direction, 5. And we're going to multiply that by the total time, 1.77. And plugging that in, we get 8.85 meters. That's how far our soccer ball goes. Okay? So again, steps that we need to use. Draw a picture. If we're given an initial velocity, we need to find the components of that velocity. Make a variable table, being very specific what we're making a variable table for. Fill in the x and the y, and figure out which kinematic equations are going to allow us to get what we want. All right, so the answer then to how far was 8.85 meters. Sometimes how far is also called the range of the projectile, back from artillery days. All right, let's do one more example, and we'll call it good. Okay, in this example right here, let's say that we've got a ball that's rolling off of a tall shelf. And this tall shelf is 2 meters high, and the ball rolls off the shelf with a velocity of 5 meters per second. So here, that initial velocity is completely horizontal. Okay, we know that the path the ball takes is going to be half a parabola on the way down. It's going to hit the ground down here with some final velocity, v final. But that initial velocity is still going to be 5 meters per second horizontally, but there's going to be some vertical component that we would need to add in if we wanted to find the magnitude of the final velocity. So let's do two questions here. Question number 1, we want to know how far from the base of the shelf does the ball land. Okay, so that's going to be our x final. And we also want to know, what is this final velocity? How fast is the ball going when it hits the ground? V final. All right, now I'm not just asking for the y component. I'm not just asking for v final in the y direction, which is now this blue line right here. All right, I'm asking for the black one. I'm asking for the total, the vector sum of the horizontal and the vertical. Okay, so we're going to do a variable table. We'll do it over here this time. And this is going to be the total flight from the shelf all the way to the ground. So x, y, let's fill them out. So I am going to do something interesting. I'm going to make my origin the 0, 0 point right here. So this is x equals 0 and y equals 0. All right? And that's going to make my initial x position, x naught, 0 meters. And it's going to make my initial y position positive 2 meters. If I put my origin up where the ball was launched from, the only thing that would change here is that y naught would have been 0, y final would have been negative 2. So filling in the rest here, we have x final is something we're trying to find. Velocity in the x direction, it's launched completely horizontally, so it's 5 meters per second. The time that it takes is unknown. Y final, the ball hits the ground, so it's 0 meters off of the ground when it does that. V initial in the y direction, the ball is launched with an only horizontal velocity, so it has no y velocity. This is like looking at a ball at the top of its parabolic trajectory if we launched it from the ground. No velocity at the top. Velocity final in the y direction is something we're going to need to find. The acceleration is negative 9.8 and the time is unknown. Remembering again that those two times are the same. We're talking about the total flight of the ball. So let's see, I got two unknowns on the x side, can't do anything with it. I have two unknowns on the y side, but I do have an equation that has v final in it but does not have the time in it, and that's the v final squared equation. So let's go ahead and plug that in. We have v final y squared is equal to v naught y squared plus 2 times a times delta y. So here we would be solving for v final in the y direction. So we've basically already got it solved there. We just have to take the square root of both sides. So v final in the y direction is going to equal the square root of 0 plus 2 times negative 9.8 times delta y. Careful here with the signs, because y final is 0, y initial is 2. That negative is going to cancel out the negative from the 9.8, so we don't have issues with a negative under the square root. Let's throw that in the calculator and see what we get. I have an answer of 6.26 v final in the y direction, and that would be meters per second. And you think, wait a minute, down here at the bottom, that final velocity should be negative. But I say, remember, anytime you take the square root, you get a plus or a minus. So I'm going to take the negative answer. So this is negative 6.26 meters per second. And we plug that in. Now we still need to find out what that x final is. And actually, we still need to find out what the final velocity overall is. So to find out what that final velocity overall is, we do some vector addition. We know the horizontal is 5 meters per second. We know the vertical is down at 6.26 meters per second. And so we've got to use the Pythagorean theorem to find out what the magnitude of this v final is. And then we're going to use the inverse tangent to find out what theta is. I'm not going to waste our time doing that here. Straight up vector addition to find v final. All right? So more interesting, let's find some time and then find out what x final is. So to find the time, here we're going to use the simple equation. V final, let's try that again. V final in the y direction is equal to v naught in the y direction plus a times the time. So here we're looking for the time, v final y minus v naught y all over a is equal to t. So v final in the y direction, I got to go back and look, it was 6.26, negative 6.26, minus the initial velocity in the y direction was 0, divided by negative 9.8. That's going to equal the time. Plugging that into the calculator, we've got 0.64 seconds is our time to fall down. Now we need to find out what x final is. So x final is equal to x naught plus v in the x direction times time. Now we know what v in the x direction is. It was 5. The time we just found was 0.64, and the initial position was 0. So x final is equal to 0 plus 5 times 0.64. We plug that in and we find out how far away that it was from the table, and we're looking at about 3.2 meters from the base of the shelf. Okay? So again, draw a picture, make a variable table, figure out which kinematic equation is going to help you find what you're trying to find. Most of the time you're going to be working with the y variables first, because you're usually going to have two unknowns in the x. All right? We'll see you next time.